I'm pleased to have everybody here at the Midwest Computability Seminar. Leszek is going to talk on the reverse math of combinatorial principles over a weak base theory. And I'm not going to butcher his last name, so it's all yours.
Thanks a lot, Peter. Thank you very much for the invitation. I'll talk about some particular pieces or parts of some joint work that we have been doing. I guess the whole project is joint with Marta Fiori-Carones, who is a postdoc in Warsaw right now, Kasia Kowalik, who's my PhD student, Lawrence or Tin Loc Wong, who's in Singapore, and Keita Yokoyama. This stuff will end up, some of it's been written up, some of it is being written up. It'll end up in more than one paper, and the papers will have different sets of co-authors, but I would say the whole thing is joined with that group. And it's a piece of work in reverse mathematics. I guess that most of you know at least the general idea of reverse mathematics, but well, yeah, the idea is that you study the strength of axioms to prove, needed to prove some theorems of what one could call ordinary mathematics, so not high set theory, but say things from analysis, topology, combinatorics, whatever. And you do this by, well, formalizing them in a suitable language, choosing a basic axiom system that you'll use to compare these theorems. That's called the base theory, and we'll get to that in a moment. And then you prove implications between these theorems or equivalences between them, or even better, equivalences between the theorems and some known, well-understood logical principles that say that, for instance, some particular sets exist or something like that. And this is strongly connected to computability theory. Maybe I should say to those who don't know me, I'm not a computability theorist by any stretch of the imagination, so I'm almost completely ignorant of computability theory, but reverse mathematics in general is tied to computability quite a bit. And one link that there is that the theorems that people study are often pi-1,2 statements. So for every set of naturals, or real if you prefer, there is a set of naturals. For every x, there's a y. And the strength of the theorem in terms of what sort of axioms you need to prove it is often related to how difficult, in the recursion theoretic sense, it's to compute why the solution to the problem or the witness to the theorem, given an instantiation of the universal quantifier, the x.
So one thing to say with this analysis is that they are sensitive to population, so there's definitely something to think.
And it used to be, that's what happened in the early days of reverse mathematics, say the 70s, 80s, something like that, that lots of theorems were studied, and most of them turned out to be equivalent, either provable in the base theory that I'll discuss in a moment, or equivalent to one of a small number of well understood logical principles that typically had a clear computability theoretic meaning. Well, for instance, these principles could be like, for each set, the jump of that set exists. And later, the picture got quite a bit more messy. So starting, I guess, mostly in the 1990s, people started studying theorems from combinatorics a lot, in particular from Ramsey theory. And there it turned out that this neat picture no longer holds. Basically, if you look at various Ramsey theoretic statements, they're typically pairwise inequivalent. Small variations change the strength of the theorem. And they form a very complex, complicated web of implications, non-implications, and so on, which gets called the reverse mathematics zoo sometimes. So I guess that's an analogy to the complexity theory zoo from computational complexity, but I didn't come up with the name, so I'm not really 100% sure. Today's talk will have a slightly unusual emphasis for a talk in reverse mathematics. We will focus on the base theory, and we'll consider a weaker base theory than the one that gets studied the most. So what is the usual base theory? The usual base theory is called RCA0, where this stands for recursive comprehension axiom, recursive in the sense of computable. I would like to spend as little time as possible discussing the syntax, the kind of syntactic details, but the basic idea is that you have two sorts of variables. One is for natural numbers. We'll use lowercase letters for those. You typically call that the first order sort. Then there's another set of variables. We'll use uppercase for sets of naturals. That's the second order sort. And you've got, say, basic symbols to represent arithmetical operations. And you've got the set membership symbol between a natural number and a set. And the axioms of this theory are, well, some basic axioms about the arithmetical operations. Then you have delta 1 comprehension or computable comprehension. If you've got some guys that are already sets, and you've got a computable property relative to those sets, well, this is properly given by suitable logical syntax, but never mind. Then if you have this computable property of natural numbers relative to some x's that already are known to be sets, then the collection of those natural numbers that have this property is a set. So there exists a set of those guys that have this property. And we also need some sort of induction axiom if we want to talk about the natural numbers. And this might be a bit of a surprise if you're seeing this for the first time. We don't have induction for computable properties, but we have induction for CE or RE properties. So if you've got some sets and you've got a property that's defined by a sigma 1 formula using these sets parameters, so it's recursively enumerable relative to those sets, then you've got induction for it. So the sigma 1 might come as a bit of a surprise. There are sound technical reasons for having the sigma 1 here, but nevertheless, it might be slightly surprising. And as a matter of fact, because the idea is that this recursive, this RCA theory formalizes a kind of computable mathematics, so you might think that the induction axiom is maybe a bit strong. And in fact, people have considered a weaker theory. This theory is named RC0 star, and it's formalized just the same as RC0, except that you weaken the induction axiom. So you only allow induction for properties that you know to be computable relative to some things that are already known to be sets. So you weaken the induction. This theory is much less studied than the usual one. It's pretty old now. I mean, it was introduced in the mid-80s by Simpson and Smith. It has been studied a bit. I mean, the number of papers about this is probably like high single, low double digits, or at least that's the number of papers I'm aware of where this sort of makes some sort of not completely trivial appearance. It has been studied both in a more or less traditional mathematics, reverse mathematics setting where you study typical maths theorems. And it has also been studied in a subfield that you could call reverse recursion theory. That's actually named, has been applied to it, where you want to understand how much induction, for instance, is needed to prove various results in recursion theory. And most of the results about this theory, not all, but I can think of one exception off the top of my head, at least the classical results about this theory, have one of two forms. Either a given implication or equivalence still holds over this weaker base theory, RC0 star. For instance, it's a non-trivial result of Chong and Morad from the early 90s that the Friedberg-Muchnik theorem still holds over this theory. And the other kind of result is that over this base theory, this weaker base theory, such and such a statement is actually equivalent to sigma 1 induction, so to RE induction. So it's equivalent to the stronger base theory. For instance, various theorems from algebra are known to have this property, but there are quite a few examples. So, as I said, typically these days, or often these days, reverse mathematics is about combinatorics, and examples from this Ramsey theoretic zoo that I mentioned. I would like to illustrate what I'll be talking about by four main examples of principles whose strength we might want to know. Ramsey's theorem for pairs, which says the usual thing. If you've got a two-coloring of pairs of natural numbers, then there's an infinite homogeneous set. So on this set, the color of each pair from that set is constant. A weakening, a special case of Ramsey for pairs, which is the so-called chain-anti-chain principle, CAC. That says, it's a typical, I guess, exercise application of Ramsey's theorem. that if you've got a partial ordering on the naturals, then there's an infinite chain or an infinite anti-chain. Then there is a principle which is weaker still, in fact, ascending descending sequence principle, which is about linear orderings. If you've got a linear ordering, say on the natural numbers, then there is either an infinite ascending sequence in it or an infinite descending sequence in it. And finally, something that's perhaps less widely known for people who don't study reverse mathematics as such, there's this thing called cohesive Ramsey's theorem, and this says that if you've got a two coloring of pairs of naturals, then there's an infinite set which might not be homogeneous, but on which the coloring stabilizes. So if you take any element of that set, say X, then the color of the other elements of the set with respect to X will, from some point onwards, be constant. So there is a Y such that for all guys above Y, called them Z, that come from the set, the color of X and Z will be the same as the color of X and Y, X and Y. So I don't have a very good justification for choosing these particular principles. I would say that, well, they're all consequences of Ramsey. They're all the three weaker ones, the orange Ramsey, are actually known to be one half of a certain decomposition, logical decomposition of Ramsey's theorem, and they typically tend to be viewed as maybe the weaker half of that corresponding decomposition. And finally, over RC0, they're nicely linearly ordered. So maybe that's reason enough to study those guys. Most of this work on the relationship between these principles was done by Dennis Hirschfeld and by Richard Shore in a 2007 paper in the JSL. And these implications, Ramsey implies chain anti-chain, this implies ADS, and that implies cohesive Ramsey. They're known to be strict. And most of the strictness was proved in Hirschfeld Shore as well. Some of it was in a later paper by Lerman, Salomon, and Tausner. So the question for today is, how do these guys behave over our weaker base theory? And as you can imagine, I guess, if the base theory was weaker, that might mean that maybe some implications will break down. And moreover, it might happen that a principle that is somehow easy to state in an informal way, and it's obvious how to formalize it over the stronger base theory, it might actually start falling apart into possibly inequivalent versions over the weak base theory. And in fact, this is what happens here. So what happens here is all of these principles say that for every coloring or coloring of some sort, at least, there is an infinite set that does something. Well, in the case of Ramsey, it's homogeneous, and in the other cases, it's something weaker. And it turns out that failure of sigma-1 induction means that the notion of what it means to be an infinite subset of the natural numbers becomes a little bit problematic, and we have to spend some time discussing that, because that really matters for this setting. So if you've got a model of this weaker base theory, RC0 star, that's not a model of the stronger one, RC0, then that means exactly that induction for some sigma-1 property fails. Now, failure of induction basically means that there is, in this model, the model, I will denote models typically as mx. M is the first order part of the natural numbers, or what the model thinks to be the natural numbers. And x is what it considers to be the power set of the natural numbers. So the script x is the second order part. So if you've got sigma-1 induction failing, then that means that there is a so-called sigma-1 definable proper cut, meaning there is a definable subset of the natural numbers, actually sigma-1 definable, that contains 0, it's closed under successor. We can actually assume that it's closed downwards, and I will. And it's proper. It's not the entire natural numbers according to the model. And that's almost by definition what failure of induction means. But moreover, there is also a related phenomenon. So there is also an infinite subset of the natural numbers that the model recognizes as a subset. It's in this what it thinks to be the power set of naturals, where infinite here means unbounded. Let's call the set A. So it's cofinal in the natural numbers. And this set has, you could say, smaller cardinality than natural numbers. So this set can be enumerated as, say, A0, A1, A2, and so on. And the indices only run up to the end of this cut J, which is proper. They don't cover all the natural numbers. So in a reasonable sense, you could say that there's a cofinal, or reasonably infinite set of natural numbers that has lower cardinality than the set of all natural numbers. The cardinality is that cut, and this can be made precise. This makes good sense. So in some sense, this is something that I always had it as an intuition, and then I realized that it's mentioned in one of the early Chong-Morad papers on reverse recursion theory. In some sense, the natural numbers behave a little bit like a singular cardinal. You've got this cofinal set of lower cardinality. That's what it means to be a model of the weaker but not the stronger base theory. So this notion of exists infinite sets such that becomes a bit delicate, and accordingly, if you take the statement that had a natural, perfectly unproblematic meaning previously, for every coloring F, there exists an infinite subset of the naturals H such that blah blah blah. It can have at least two meanings. The first one is that infinite simply means unbounded, like, for example, that set A on the previous page in the picture. So for every F, there exists an unbounded H such that whatever. This I'll take to be the normal version of a principle. I do think that these are the proper versions, the correct versions to study over RC0, but of course you can argue with that. Or RC0 star, sorry, over the weaker base theory. And there's another version where infinite could mean having full cardinality. So for every F, there exists a set H, which is infinite in the sense that it's not enumerated by a possibly proper cut, but you'll have a kth element of that set for every K in your natural numbers. So this is a much stronger notion of infinity. And we'll call this is a temporary name which might change along the way to, say, publication of the papers, but we'll call this sort of version the fat version. We've tried to call it strong, but strong has too many meanings, even in reverse mathematics, so we dropped that. We tried to call it long, but it's not really a good fit. So these H's of full cardinality, they aren't that long. They're in some sense fat, or maybe dense wouldn't be a very bad word, if, at least in the intuitive sense. The technical sense means something different. But the idea is that the set A that you saw in the previous picture, that's a really sparse set, and we want to disallow these really sparse sets in the fat versions of theorem. So this is a very important distinction. This is something that is pretty foundational for this RC0 star setting of combinatorics in reverse mathematics. I'll try to say something about each kind of principle, and we'll start with the normal ones. So if I wanted to say the most important thing, or the most important thing that we have learned about these normal versions of the principles, I'll have to introduce some basic concepts from models of arithmetic. So please bear with me. I hope you don't hate this stuff so much to switch off. It has to switch off now, but this will be really pretty basic stuff. So if you've got a model of our base theory, M, which claims to be the natural numbers, and script X, which claims to be its power set, and you've got a proper cut in this model, say call it J, there is something called cod M over J. So that's the family of so-called coded subsets of M over, or subsets of J that are coded in M. This is obtained by taking all the sets that the longer model that M believes to be sets, and just taking their traces on J. So just take the intersections with the cut. This family, it's easy to prove, but not completely trivial. Now I'll skip the proof. this family does not depend on what the model, the longer model, believes to be the power set. It only depends on the first order model, so only on M, not on script X, and it depends on the cut J. So the notation cod M over J makes sense. It's justified. And this family, cod M over J, forms something like a second order part. It consists of subsets of J, so it makes sense to consider it as a second order part of a model with first order part J. And if J happens to be closed not just under successor, but also under the exponential function, then J with this family of coded sets, it actually satisfies our base theory again, RC0 star. And moreover, it satisfies a somewhat stronger theory called WKL0 star, which is RC0 star plus this additional principle called weak-Koenig's lemma that basically says every infinite binary tree has an infinite path, where to emphasize that infinite here means of length, covering every natural number along the way, I wrote length n. So, but basically, weak-Koenig's lemma says every infinite binary tree has an infinite path. So here's the most important thing that we've learned about these normal or weaker version of the Ramsey theoretic principles. So let's say you have a model of RC0 star. Let's say you have a proper sigma 1 cut in this model, call the cut J. And take any of our principles. There is a more general sufficient criterion for this, for what I'll say to hold. You don't have to consider just the usual Ramsey for pairs. You can consider Ramsey for n tuples for larger n as well. Then the big model, the original model you started with, satisfies this principle if and only if you look at the smaller model where the cut, only the numbers in the cut are the first order universe and the coded sets are the second order universe, if and only if that smaller model satisfies C. So this is a pretty remarkable thing. And the reason it's remarkable, I think there are at least two reasons. So if you look at this equivalence, you will notice that the left-hand side doesn't depend on the choice of your cut J, as long as it's a sigma undefinable cut. And if there's one such cut, there are going to be many, a proper cut, of course. So the left-hand side doesn't depend on the cut J, and the right-hand side, pretty amazingly, perhaps, doesn't depend on the second order universe. So for this sort of Ramsey theoretic principle, I'll come back to this point. If they hold, then they hold regardless of what your second order universe is. So that's pretty striking. Now, I guess I will give you an example of how this sort of thing is proved by proving one implication from holding in the model to holding in the cut for C equal to Ramsey theorem for pairs, but I'll skip an intermediate step that I'll just mention on the way that it holds. So let's try to justify this. Let's try to see why, if Ramsey holds in the big model, then it holds on a sigma undefinable proper cut. So let's assume that induction fails. Well, okay, you've got this proper cut J. Then there is a set which is indexed, meaning increasingly enumerated by J. So if we've got the cut J, there's going to be a set A that the model M recognizes to be a set, such that A is indexed by J. A is A0, A1, little A2, little A3, and so on, and the indices run up to J. Let's say we have a function, let's say a two coloring of pairs from J, and it's coded in the model, and we want to show that there is a coded homogeneous set for this on J. So we map the coloring of pairs from J, we call that F, onto pairs from A in the obvious way. I'll call this, I don't know, check F. So if you've got two elements of A, I1 and AI2, you color them just like F of I1 and I2 were colored. So for instance, you had a red edge between 1 and 3. So let's have a red edge Did I mess up? Yeah, I guess I messed up ever so slightly. There should be something off by 1 index. So yeah, okay. So yeah, let's have a red edge between A1 and A3. This is fine. Let's have a red edge between A1 and A3. And we also have to color. We want a coloring on the entirety of the natural numbers. So let's color the pairs that come in between elements of A, or maybe below all the elements of A, by moving each of them to the next nearest element of A. So if you've got a guy between A0 and A1 and the guy between A2 and A3, you color that pair as you would A1 and A3, so as the original coloring had between 1 and 3. And this still leaves the issue of what you do if 2 elements are between the same 2 elements of A. You just do anything, don't worry about that. So if we've got Ramsey in the big model in M, then we get a homogeneous set to this for this coloring on the large model. Let's call that set H. So maybe there's some element of H between A0 and A1, and maybe there's another element between A2 and A3, and so on. H is these green points. And now there is a lemma called the Chong-Morad coding lemma that I'm skipping for the purposes of this talk, that tells you that you can map this set back to the cut, back to the set of indices, and that thing will be coded. So because there was a green point between A0 and A1, there will be a green point in your set on the cut. Sorry, at 1 will be a green point in the smaller. It will be in the set that you're mapping back to the cut. Because there were elements of your big homogeneous set between A2 and A3, that means that 3 will be in the homogeneous set on the cut, and so on. So there is a coding lemma that says that this set of indices that corresponds to something in the large homogeneous set. This set is coded and it's a homogeneous set on the cut. So this is the sort of technique that gets used here. So let me summarize what follows from this, because this is the most important thing that what we learned about these normal statements of Ramsey theoretic principles. So if you've got any principle, call it Psi, that you take the normal version of it, and it happens to satisfy that characterization in terms of cut that I gave you, that happens quite often. We have some sort of sufficient criterion for that. Then, for example, because of what I mentioned, that satisfying this principle does not depend on the second order universe, that means that if you have a failure of sigma 1 induction already in the light phase universe, so with no set parameters, already in the computable sets of the first order model, then that principle is satisfied in the computable. It's computably satisfied. So it can happen that, for instance, in models of RC0 star, you will have situations in which all computable colorings of pairs have computable homogeneous sets. So this is something that doesn't happen in the real world by a theorem of Joker's, by a very classical theorem, but to prove Joker's theorem, it turns out you need quite a bit of induction. And if you don't have it, this might fail. Another thing, this is perhaps more for the people who are really into reverse mathematics. People are very much interested in what sort of arithmetic theorems, so what sort of first order statements about the natural numbers follow from various principles. And it turns out that if you've got a principle that has this property that it's equivalent to its version on a cut, then it never proves any new pi3 arithmetical sentences. So no new pi03 sentences are provable that were not provable already in our weak base theory. This sort of phenomenon is summarized as saying that the base theory plus the principle is pi3 conservative over the base theory itself. And on the other hand, it turns out that this sort of principle is almost never conservative over the base theory for stronger first order statements. So if you want this principle to not only prove the same old pi3 theorems that the base theory did, but also pi4, pi5, and so on, then you have to know that this principle actually follows from weak Königslemma over the weak base theory. So so we have a very strict criterion for conservativity in this case. And in the particular case of the cohesive Ramsey's theorem, this shows that cohesive Ramsey is not arithmetically conservative over the base theory RC0 star. This answers a question that David Belanger asked a number of years ago. One of the things I wanted to mention, reverse mathematics should be about implications, right? So I don't have that much to say about the implications over these between these normal versions over the weaker base theory. So the implication from Ramsey to chain anti-chain and from chain anti-chain to ascending descending sequence, those are very straightforward. They don't require much axiomatic strength. They still hold here. Also, the implication from Ramsey to cohesive Ramsey holds. We don't know whether any of these principles about orderings still implies cohesive Ramsey. And this looks like a difficult problem that has some sort of finite combinatorial core. We haven't been able to solve this, at least for now. But it looks pretty challenging. So at least on one of the implications that we had seems to break down over a C0 star, but yeah, it remains to be seen. So that's as much as I wanted to say about these normal versions, but let me get to the fat ones. So the fat versions, just to remind you, say that for any instance of a theorem, typically a coloring, there is a witness to the existential quantifier, so some sort of homogeneous set that's required to have full cardinality. So not only cofinal in the natural numbers, but of cardinality, the full natural numbers. So most of these principles I mentioned have one obvious fat version. It's clear what the fat version of the principle should be. And in some cases, it's easy to see that this fat version actually implies induction. It implies the original base theory with sigma and induction. So for instance, Keita observed this about the fat version of Ramsey, which he calls the strong version of Ramsey in an early paper on this topic. There is a subtlety concerning, in particular, the ascending-descending sequence principle. So there are at least two natural fat versions of this principle, which vary according to what an ascending or a descending sequence should mean. So one way of formalizing the fat version of ADS, we call it the set version, is that for every linear ordering, there is H, which is a full cardinality ascending or descending sequence in the following sense. It's a subset of the natural numbers. It has the same cardinality as the natural numbers. And it's either an ascending sequence, meaning the strange ordering and the natural number ordering always agree on this set, or it's a descending sequence in the sense that the strange ordering and the natural number ordering always disagree. Okay, so that's one version of fat ADS. Another, which we call the sequence version, says that you've got an ascending or descending sequence in the natural sense. So for every linear ordering, there's a map from the full natural numbers into the domain of the ordering, which happens to be the natural numbers as well, which is an ascending or a descending sequence in the natural sense. I mean strictly ascending or strictly descending. So you want this map, the sequence, to be an injection. You don't repeat elements because that would be cheating. That would no longer give you a fat principle. So these are two pretty natural formulations. It's easy to check even over our weak base theory that fat Ramsey implies fat chain anti-chain, which implies fat the set version of ADS, which implies the fat sequence version of ADS. These are pretty trivial, or almost trivial in most cases to prove. And if you had the stronger base theory with sigma and induction, then the set and the sequence version of ADS actually coincide. So it's only a potential difference in our weaker setting. So let's discuss these versions of ADS, this fat ADS. So it turns out that if you take the set version of ADS, so the witness is a full cardinality subset of the naturals on which the ordering always agrees or always disagrees with the natural number ordering. This turns out to imply sigma 1 induction. So all the stronger statements, including fat CC, imply sigma 1 induction as well. I guess this is a simple proof, so I can sketch it. Let's assume that you've got a failure of induction. So we've got this proper sigma 1 cut, again, J, and we've got an unbounded set indexed by this cut. Let's call the set A, and index its elements as A1, A2, and so on, according to J. And let's come up with the following linear ordering. If you've got two different elements, X and Y, that come from, so to speak, different blocks, where the set A divides the universe natural numbers into blocks. So X is between AI and AI plus 1 for some smaller I, and Y is between AJ and AJ plus 1 for some J bigger than I. So then, if Y is above a larger element of A than X is, then just set that X is smaller than Y in this ordering. If they are in the same block of the natural numbers, so between AI and AI plus 1 for the same I, reverse the ordering. So just set X is smaller than Y exactly if X is strictly larger than Y, or larger or equal, sorry. This should be a larger and equal, a non-strict inequality, of course. So within a block of the natural numbers, you reverse the ordering. Across blocks, you keep the usual ordering. And it's easy to check that the ascending sets, in the sense that I described, if they're ascending in this ordering, then they can only have as large cardinality as the cut, so they don't have full cardinality. And descending sets, so sets on which the natural number ordering and the curly ordering disagree, they have to be within a block, so they're actually finite. So if you've got failure of induction, you get failure of this version of ADS, this fat set version of ADS. So one wonders what happens about concerning the sequence version of ADS. And I guess I'll go over this quickly. I'm a bit short on time. So to our surprise, it turns out that this weaker version of ADS that we call normal is equivalent to this version that says for every linear ordering, you've got a full cardinality increasing or full cardinality decreasing sequence in the ordering. I won't have time to go over the proof in detail, but I'll discuss the idea briefly. So there was something introduced in an important paper by Keita and by Ludovic Bataille about conservativity of Ramsey's theorem, called the grouping principle. And we introduce a variant that, well, I guess it would make sense over RC0 as well, but we really care about it in the setting of RC0 star, in this weaker base theory setting. So we call this the ever fatter grouping principle, corresponding to these fat versions of the Ramsey theoretic principles. It says the following: you've got, given a two coloring of the natural numbers, there is an infinite doesn't have to mean full cardinality for now. There might be not that many members of this family. There's an infinite family of finite sets. So G0, after which higher in the natural number ordering comes G1. It's all elements of G1 are strictly above all elements of G0. And then there's a G2 and so on and so on. And this family of sets has two properties. Firstly, if you think of each Gi as a group of elements, then if you compare two elements from pairs of elements from two different groups, say Gi and Gj, then the color of such a pair depends only on the groups. So if you've got two guys like X and X prime from G3, and you've got two guys Y and Y prime from G8, then the color of X and Y has to be the same as X prime and Y prime. And secondly, we want the cardinalities of these groups to increase, and not just to increase maybe by 1 or something, but we want to make sure that they grow to the full cardinality of the natural numbers, meaning that for every natural number, there is a group that has at least that cardinality. And then the further groups will only have bigger cardinality, so it will never decrease. So that's what the ever fatter is supposed to indicate, that these groups have ever larger cardinality and eventually exceed any given finite cardinality. Yeah, that's the idea. Okay, that's more or less the picture. So you've got some sort of, you might not have a homogeneous set for your coloring, but you have this bunch of groups. They get bigger and bigger, and the color between elements of two groups is determined by the groups. What happens within one group, we don't care. And the theorem, oh, there's something wrong with the indexing here. The 0 should be a subscript, but the theorem that we proved about this is that our weak base theory plus weak Koenig's lemma actually proves this principle. And for the particular case of the ascending, the kind of colorings that you get for linear orderings, so for the ascending descending sequence principle, actually you don't need the weak Koenig's lemma. So I'll skip this proof. I'll just say one thing about it, namely, we had another paper on Ramsey's theorem and understanding its logical strength over the usual base theory with Keita, published recently. And in that paper, we studied a kind of maybe somewhat new technique in which you somehow thin out your set first from below and then from above to get some sort of more homogeneous set. And this mattered for proving, say, bounds on Ramsey numbers in an unusual setting where you measure the size of finite sets. So it's like a finite Ramsey theorem, but the sets, the finite sets don't just have a finite cardinality, but they have a size given by an infinite ordinal. So we proved some upper bounds on the Ramsey numbers in that particular setting, and that meant something for the logical strength of Ramsey's theorem. And it turns out that the same technique appears here to prove this particular version of the grouping principle. I'll skip it completely. And then somehow using this grouping principle and using the weakest possible, so this normal version of ADS, you can prove the fat ADS, at least for the sequence variant. For the set version, this fails. So a similar argument applies to cohesive Ramsey, although there we don't know whether you can eliminate weak Koenig's lemma from the proof of the corresponding grouping principle. So fat cohesive Ramsey, which has like one natural version, might not follow from cohesive Ramsey over RC 0 star, period. It follows from weak Koenig's lemma plus RC 0 star. So here's a summary of what we know about these normal and these fat principles. The picture at the outset when we started working on this looked pretty terrible. It was a real big mess. It's much cleaner now. In particular, most of these fat principles simply disappear. They turn out to be equivalent to the corresponding Ramsey theoretic principle plus ADS. With the exception of the sequence version of ADS, the fat principle turns out to be equivalent to the basic, to the normal version. And fat cohesive Ramsey might be a little bit stronger than normal cohesive Ramsey, but there is a reverse implication over RC, over weak Koenig's lemma. So over RC 0 star, you get this picture. There are the fat principles, which typically either imply sigma 1 induction or are basically equivalent to the normal principles, either exactly or over weak Koenig's lemma. And then there's this missing implication between ADS or CEC for that matter and cohesive Ramsey. We don't know that. So these are the two main parts of my talk. Okay, I'll wrap up with two further things. So firstly, there is a stronger version of cohesive Ramsey, which is called the cohesive principle. And that one says that given given a family of sets of naturals indexed by the naturals, say Rx for each natural number x, there is an infinite set that's it's so-called cohesive for this family, meaning for every x, either almost all elements of the set are in Rx or almost all elements are outside of this Rx. So this is a sort of strengthening of cohesive Ramsey, where the color given by one element x, and you vary the second argument, it must stabilize on the witness set, on the set that you're claiming to exist, not only for x coming from that set, but from any x. So this principle is kind of strange, even if you don't require this solution, this cohesive set to be in itself fat. There is some sort of fat aspect to this principle, namely, you require it to work for every x, not just for the x's in the set, which might be a very small collection. The set might be infinite but small in some sense. So it's kind of strange. We don't know how it relates to the other principles. The main thing we proved about it, and this is kind of interesting, I guess, is that this guy is never computably true, even over our weaker base theory, which in particular means that the cohesive principle doesn't follow from Ramsey for pairs over C0 star, because Ramsey for pairs can become computably true. This guy never does. And we don't know much more. I'll skip the proof. It's by carefully observing and somehow, somewhat non-trivially, but it's not a very, very hard proof, changing some proofs of some properties or implications from the cohesive principle that worked over Z0, you prove that something still works over C0 star, and that's enough to show that. That's enough to show that this cohesive principle can be computably true. And they have one, okay, so here are some open problems. One thing that we don't know, I mentioned, was that we don't know whether these principles about linear orderings imply cohesive Ramsey over our weaker base theory. Another thing is whether this grouping principle that I mentioned, whether it can be proved assuming our base theory and not induction, but ignoring weak Koenig, without assuming weak Koenig's lemma. So that would, for instance, collapse these two variants of cohesive Ramsey that I mentioned. So that would mean that fat cohesive Ramsey and normal cohesive Ramsey are the same thing. We don't know that. And the third thing that seems pretty intriguing and possibly hard is what the strength of the cohesive principle is. It could be anything. It could be just barely stronger than the base theory, or it could be as strong as to imply the stronger base theory. I mean, it could imply sigma-1 induction, and we know neither, and it's not clear what the case is. So here's our final slide. It was not clear to me whether to include this, but I would feel a little bit, I'd say dishonest, or I'd feel like hiding something if we did not include this. So we decided to mention this towards the end of the talk. This is a sort of stop the presses slide about things that we've only discovered rather recently, and we've just started writing them up. So these are more technical things, perhaps, for people who are actually deeply into reverse mathematics. But this characterization of conservativity that I mentioned, that if you have a Ramsey theoretic statement, then it's pi11 conservative over RC0 star, if and only if it follows from weak Koenig's lemma. This actually holds true for all pi12 statements whatsoever if you add a not induction to the base theory. So pi11 conservativity over RC0 star plus not induction is the same thing as being a consequence of weak Koenig's lemma over not induction. So in particular, that means that in models of not induction, where you don't have sigma 1 induction, typical forcing arguments will fail. Basically, any forcing argument that would produce anything beyond branches in trees, in binary trees, will fail. This thing is false if you don't have the not induction in the base theory. So if you just consider conservativity over C0 star, then there will be conservative principles that don't follow from weak Koenig's lemma. And the results you get here, they spill over to a more traditional reverse mathematics setting where you consider, for instance, RC0 plus so-called sigma 2 collection, which is the same thing as delta 2 induction, and not sigma 2 induction. It turns out that, for instance, there is a maximal theory consisting of pi 1, 2 sentences that's pi 1, 1 conservative over the sigma 2 collection and not sigma 2 induction. And it's recursively axiomatized, surprisingly. So we would have expected that it's pi 2 complete, but it's not. It has a recursive axiomatization. This also says things about what sort of techniques may work and will not work about proving conservativity over this sigma 2 collection thing. So for instance, for the particular case of Ramsey's theorem over RC0, where it's not understood what the arithmetical consequences are, or the pi 1, 1 consequences are, we now know, we have a result saying that it comes down to the pi 5 consequences, so to speak. So if all the pi 5 consequences of Ramsey are provable from sigma 2 collection, then all the arithmetical consequences of Ramsey are. And there's stuff coming as well, but this is, as I said, this is like a stop the presses kind of thing. This will take us a while to write up. Thanks a lot. Sorry for going a bit over time.
No problems. It was a nice talk. Thank you. We're going to open up the floor for questions. People could just unmute themselves and ask a question, please. Or they could raise their hand. If no one has a question.
I have a question.
Hi.
Do you have any candidates in mind for a possible decomposition of RT22, you know, like Co plus SRT22, but works over RCA0?
Well, cohesive Ramsey plus stable. Do you mean that works over RCA0 star, or?
Yes, I misspoke. I meant to say RCA0 star.
Right. So of the usual decompositions, meaning EM plus ADS, whatever it is, I guess something that gives you semi-transitive colorings plus CAC, and the cohesive principle plus stable Ramsey, all of them except the last one work. And actually cohesive Ramsey plus stable Ramsey does work. Cohesive Ramsey is a consequence of Ramsey. So this is, you know, from a purely combinatorial point of view, the decomposition of Ramsey into the full principle Koch, the cohesive principle, and SRT22 is something kind of surprising. So it's a non-trivial fact that the cohesive principle follows from Ramsey. The combinatorially obvious decomposition is into CRT22 and SRT22, right? Into stable and cohesive Ramsey. And that works. The surprising fact that you get over RC0 stops working here. Was that what we were asking about?
Yes, thank you.
Thanks.
Other questions?